All right, officially welcome to our session 2 evening review session, where tonight's topic is going to be dealing with tables and Riemann sums. And as I was telling the participants before we started to record here, we are going to be focusing on two problems in particular from two recent AP exams, the first of which is this 2016 storage tank problem. So without further ado, let's go ahead and read through this. It says that water is being pumped into a tank at a rate modeled by W of t is equal to 2000 e to the negative t squared over 20. And that's measured in liters per hour over the time interval 0 to 8. T is measured in hours, of course. Water is going to be removed from the tank because, what else would it do, at a rate modeled by R of t liters per hour, where R is differentiable and decreasing on 0 to 8. Selected values of R of t are shown in the table. And we know at time t equals 0, there are 50,000 liters of water in the tank. Guys, that is a lot of text. That's 4 lines of a ton of information. And I know that it can be very overwhelming. Don't worry about it. You're not going to have to digest every single word of that problem in the first part. Let's read this first part and sort of kind of figure out where we're going to go. It says, estimate R prime of 2 and show the work that leads to your answer, and then indicate the units of measure. And what we're going to do here is just kind of think about this a little bit. You can ignore this little timer. That's something that I use in my particular class. I just didn't delete it. So we're going to try to take the derivative of this function called R. So yeah, okay, well, here's R. So let me get this straight. Problem, part A, you're asking me to take the derivative of a chart, of a table of values, and of course we can do that. We have to be sort of clever about it, and if you guys learned anything from your first semester, you know that derivative means slope, right? Slope of a tangent line. The only problem is we can't really do a tangent line here. We don't know what's truly happening when t is 2. We know it's somewhere right around in there. So we can do the next best thing. We can use the slope between 2 points. That's actually called a secant line. So we can just take these two y values, and of course these two x values, and we can put them in what's called a difference quotient, and we can come up with an answer. Now, I don't think that's really difficult to do, because we're going to say R prime of 2, and I'm going to use an approximation symbol. I don't want anybody freaking out by this. We're going to talk about that in a second. It's not required. And to do like the minimalistic amount of work possible, just pick whatever order you want to subtract. I'm going to take the 950 first minus the 1190, and then we'll divide that by, well, the top would be 3 minus 1. I need to make sure I take that same order, 3 minus 1. And once I do, I'm in pretty good shape because I've got something that's very numeric. I got something that's really going to work for us. Now, that being said, what if a student was really interested in going a little farther with this? Well, you could go ahead and subtract the tops, right? A 950 minus 1190. What would that be? Well, that's a tough one. That would be, let's see, that would be, I'm saying negative 240, is that right? Over 2. And then you could go even further if you wanted to. You could simplify to negative 120. However, none of that is required. None of that is going to be required because your obligation is to get something that's numeric. And once you do that, you've got the point for the approximation. So any of these things that I circle will be acceptable for the numeric answer. And I think you guys have probably been told that time and time again. All of your teachers are very well aware of that. Now, there is one thing that you do need to put here, and it does say indicate the units of measure. So you could very much risk losing a point if you don't have the units of measure. And if you take a look at this, you think about what does the units of R of t look like? Well, they tell us that's liters per hour. That's really what this numerator is all about, right? That was, a pair of R values that were subtracted, so I'm still dealing with liters per hour. But if I'm dividing by another factor of time, hours, that would make my new label liters per hour squared. And it is also perfectly acceptable to say liters per hour per hour. You can also abbreviate to your heart's content. Just try not to take too much of a chance on abbreviating something very strangely. You're probably better off writing out the words when you have the time. But liters per hour squared is certainly going to work. And I would say that this would be a pretty good solution. Now, what about this guy? Do you have to have it? Typically, no, you don't. But your teachers are probably pretty adamant about trying to get you guys to show good notation, make sure that you identify what it is that you found. It doesn't take a lot to realize that's what we're looking for, r prime of t. I know that you're going to be very, very tempted to put an equal sign there. They're not going to penalize you for that. Technically, it is wrong because you are estimating, but we're going to look the other way in situations like that. If you want to take a look at the scoring rubric, we'll do that very quickly. We like to do that part by part. So if we take a look at this guy here, you can see that they pretty much have what we have with, okay, the addition of this part. Wow, what's up with that? Well, that's basically the function notation for what we just calculated. Now, does a student have to have this? And the answer is no. If you entered the problem right here as we did, you would be fine, because the key is that you must show this thing that's called a difference quotient. That might sound like a really fancy schmancy phrase, but I think all of you understand the meaning of the two words. Difference has something to do with subtraction. Quotient has something to do with division. It's basically what a slope formula looks like. Now, you cannot, this is very important. Let's say you want to write this step that I'm highlighting. All right, let me erase this piece here. You cannot stop there and expect to receive full credit. That would not give you your estimate point, because you still need to extract values from the table to figure out R of 3 and R of 1. Okay, so the minimalistic answer might very much look like what we had. Okay, well, there's a lot of highlighting on that, isn't there? So negative 120 liters per hour squared. At any point, if any of you have a question about a solution, if you need us to kind of go back and maybe emphasize some things, repeat some things, feel free to mention that in the chat. And hopefully everything is running okay with the internet. I'm getting a message every now and then that says I'm dropping some frames and the internet's unstable and the world is falling apart around us as we speak. So I don't know if that has to do with the weather, because it's raining here in Avon. All right, let's move on to part B. This is kind of the crux of tonight's lesson. You know, it's called tables and Riemann sums. Now, I don't want you all to think that means, okay, every time you see a table problem on the AP exam free response, you're going to do a Riemann sum, because that's far from the truth. It's very common that a Riemann sum is going to be accompanied by a table, and we feel that Riemann sums are fairly plentiful on the AP exam, that it was definitely worth an entire evening of content. So that's why we named it as we did, tables with Riemann sums. But it's quite possible, if you tune in next Thursday night when we talk about some miscellaneous topics, we may see some more table problems, but they may not necessarily be connected to parts that have Riemann sums. So this one says, use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. And then we got some other things to do. They're asking us, is this an overestimate or an underestimate of the total water removed? And of course, you're going to have to give a reason for your answer, right? Your 6 favorite words. Give a reason for your answer. So we have to really understand the idea of the Riemann sum. 4 subintervals. Now I know that you, if you have the document with you, you have the table. I unfortunately have to scroll up to get this table. That's going to be kind of a pain. So give me a moment and I'm going to copy this into that box below. All right, boy, you gotta love the snipping tool. My favorite thing, snipping tool. All right, and paste. This thing might be large. Okay, it's huge. There's large and then there's huge. That's called huge. So let's drag it by the corner and make this guy a little smaller. So hopefully you guys are able to see the table there. Trying to look at my monitor, and it's showing up as well. All right, now I don't have to scroll back and forth. Great for me. So what we're going to do here is we're going to take the fact that there's 4 subintervals, and wow, what a great number to allow us to use here. 4 subintervals, from there to there, from there to there, from there to there, from there to there. This problem would not be fun if there were 5 subintervals. This problem would not be given to you with 5 subintervals, so don't worry there. So we look at this thing and we think, okay, left Riemann sum, right? What that means is we need to use the very far left sides of each of these partitions to figure out the height, right? You don't necessarily need to graph this, but you know, if you had your 1 here and your 3 here and et cetera, et cetera, et cetera, you would basically see that starting at 0, we have some y value up here at 1340, which I can't even begin to locate. That's way up there. But then this guy only goes up to like 1100. Well, we're going to have to cap off this rectangle on that left side to make this a left Riemann sum. And it turns out that that y value right there will correspond with this first entry here. So to really simplify it for you all, we use these 4 numbers for those heights. We won't use the 700 for a left Riemann sum. Now, do you all think we would use the 700 if this problem asked for a right Riemann sum? Yeah, you're smart people. You know that, right? You would definitely use the 700 and you would leave the 1340 at home. So these 4 numbers would comprise the right Riemann sum. All right, so with that in mind, we can go ahead and start assembling. We can start assembling our particular expression. Now, we want to understand too that we're trying to figure out an estimate for the total amount of water that's removed from the tank. And we have a saying at Avon High School: anytime that you want to find a total amount, you integrate the rate. Kind of rhymes, right? It's kind of easy to remember. Integrate the rate. And it's very clear that R of t is already a rate. So by integrating that rate with respect to t, and doing so during the 8 hours, so let's start at 0 and go to 8, this is going to be what we want. This is going to be the total amount of water removed from the tank. Obviously, the problem that we have here is we can't integrate some equation conventionally because we don't have an equation. So that's why we rely on this Riemann sum. And since this is an approximation, we could use the approximately symbols. I don't want you all worked up over that, like I'm never going to remember to put that on the AP exam. Trust me, Mr. Passwater and I will both attest, we grade very few problems where students write that, right? Most kids are just going to start right now with the next few numbers I'm going to write. It's okay. It's not the best practice because we'd like you to identify the work that you're doing. Like I said last night, some of you may go on to careers in STEM and engineering and math where you have to communicate math, and it's great to use good symbols so that you can convey your message a little bit better. So we're going to take the width of the first rectangle, which would certainly be 1, the gap between 0 and 1, and we're going to multiply that by 1340, and then we just keep the process going. The next width would be 2. How I get that? As I go from 1 to 3, multiply by 1190. The next width from 3 to 6. Wow, these widths are not very consistent, are they? That's going to be very common. You're not going to be able to sort of factor out a common width. You're going to have to write it each time, unfortunately. And then we get to the last width, which is 8 to 6, which is a 2, and that'll get multiplied by 740. Now, what if we stop right there? Would we get credit for what's referred to as the left Riemann sum? And the answer is yes. There's a whole heck of a lot of simplification that has not been done right there, and I think you'd all agree. But there is absolutely nothing wrong with leaving your answer like that. A lot of students will do that. Some students just aren't wired that way, and they want to find some numerical answer. Well, okay, let's say we find this numerical answer, and I'm not going to show you the calculator demonstration of this because I'm going to assume that you're all pretty good working with multiplication buttons and plus buttons, but your answer that you would get is 8,050. I'm sure that you're all going to trust me on that. If you want to check it later, go right ahead. But 8,050 is no better of an answer than the one on the line above. But what 8,050 can at least do is kind of give you an idea, you know, is your answer going to make sense? You know, if you got an answer like 12 million or something, it probably isn't likely that there's going to be that much water in the tank during that certain period of time, okay? One other thing I want to point out, this is one of the things that sometimes teachers don't like to tell their students. Maybe Mr. Passwater might jump on here and say, hey, don't tell them this. But it is possible during this mess up here that you might make a mistake. I don't know. What mistake are we talking about? Maybe you subtract 8 minus 6 and get 3. Hey, it happens, right? If something like that happens that's pretty tame, you can still earn the point for the left Riemann sum. So, you know, it's not like everything has to be perfect. You just have to look like you know what a left Riemann sum is, and you're putting that together. And the second thing that is so very, very important, I need you to really focus in on this. Look how I've written this first line as the product of two things added to another product of two things, et cetera, et cetera. We sometimes call that the sum of products. It's vitally important that you show that on your paper. The temptation is to look at this and say, hey, I'm smart. I've got a really good graphing calculator, right? And you would think that, hey, I'll just throw this into a calculator. Well, the problem with that is, you know, yes, this is a calculator problem. I'm not going to deny that. It's number one. But if you put too much into the calculator, you will not have shown that product of, or that sum of products like we need. You very well may have the correct answer, but you would not earn what's called the left Riemann sum point. All right, and when we show the scoring rubric, we'll focus on that again. It does not say, does it say in this problem that we need a label? That's an interesting point. I don't see it saying include your label. What is your take on that? Do you want to live life dangerously and just not put a label here, or what do you think? It's probably a good idea to put the label. All right. You might be okay without it, but why take the chance? Now, the label that we want here, because we've integrated liters per hour, and we've sort of, well, I guess I could say this, we've got this liters per hour right here, and then this multiplier of dt is sort of like another hour, if you think about it, will lead to hours canceling, and then you get a very logical label, right? Liters makes perfect sense because it asked for the total amount of water removed. Now, there is another piece of this, and it does ask, is this an overestimate or an underestimate? And the way that you want to think about that is what kind of behavior that the function is going to yield. And in the original stem of the problem, remember all these words that we were so kind of anxious about? Well, if we go back up here, we read some things, and we read this sentence right here, this phrase right here, that R is differentiable and decreasing. Right? Now, to kind of get a visual of that, and again, this is probably something that you would not have put on paper, but let's think about what a decreasing function might look like. Well, we know what that looks like. It might look like this, right? It doesn't have to always be con up or con down, but it might look like that. Well, think about if we start partitioning this off in a few rectangles, and we do so with the left endpoint over and down, and the left endpoint over and down, what kind of estimate do we have? Well, then the area of each of these rectangles is going to exceed the area under the black curve, right? Just by a little bit right there. And you can see maybe even a little bit more. And if I continue, it might be more pronounced. So we would just simply want to say that this is an overestimate. Let me keep the same color here, not that kind of pen. Let's do this kind of pen. So we would say that this is an overestimate, but that's not alone going to cut it, overestimate. We have to state the reason. So we have an overestimate, mute here, because, nothing wrong with using B/C for because. I see it all the time on the papers that I grade. And we'd say that R is decreasing. R as a decreasing function would be also appropriate, but as long as you have the main idea that R decreased, that's okay. And you need that. You need that information. You have to tie these two ideas together. All right, let's take a look at the scoring rubric. We didn't really announce how many points this was worth. You're going to see it. It was worth, drum roll please, I can tell you're excited, it was worth 3 points. It was definitely worth 3 points. The first point would be that left Riemann sum. Now again, students would not have to write this step. Again, I'm trying to show you like the minimalistic approach where you don't have to write as many steps. But if you choose to write a sort of a function-oriented setup, you can't earn the estimate point. You would earn the left Riemann sum point for this, but you don't get the estimate point until this is strictly numeric, and it would be on this line that I'm sort of hovering over, and we already talked about how that would be acceptable. You could go ahead and simplify it to 8,050. By all means, please use your calculator if you decide to do that. I don't really see a label point here, but we're going to play the game like the label was required. So there's our estimate point, and then, wow, talk about minimalistic. They pretty much did what we did. Overestimate, R decreasing. All right, so hopefully that makes sense. I don't see any questions in the chat yet, so we'll keep pushing on with part C with this problem. You'll notice that I've retyped the stem of the problem on this particular page so you don't have to flip back and forth. So now we're going to use the answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So we got to think about total water. Total water. I don't really have a variable name for that, so I'll just call it total water if you want to do that. All right, so let's think about this. Total water at when? Oh, at time 8. So we got to think about what this tank looks like. We go into work this day. Time is 0. We look at the tank. What do we see? We see 50,000 liters of water. That water is there. We have to start with that water. So what a great thing to do. Use 50,000 to begin this expression. Now, as we talked about this already, we see that the water is being pumped into the tank by a rate that's modeled by this particular function. So if we want to accumulate more water, we want water coming into this tank up to time 8, then we could just add the definite integral from 0 to 8 of this rate, and that's what it is. It may not look like a rate. Maybe you don't see a derivative notation around this, but that doesn't mean it can't be a rate. You want to read through the problems, read the words around the function. So once again, we integrate a rate, we get the total amount. All right, so I want you to all realize that what I just wrote here represents the total amount of water pumped into the tank. I got a lot of water now. I got that 50,000. I've got this new accumulation up to, again, time 8. But it says we got to use our answer from part B to find the total amount of water in the tank. And part B said what? We were losing water, right? Water was being removed from the tank somehow. Maybe there was a plug in the bottom. And we found out that that answer was 850. Now, that being said, it probably makes a lot more sense that we simplified that expression from part B and didn't have to write this long old sum of products to depict that 8,050. That would take care of your total water, guys. That would be the total water that's in the tank. If that would be the setup, I'm sorry, that's not your final answer, but you're going to get a point for that. So what you would need to do now, and again, I'm going to make an assumption here that we're all pretty comfortable on using the graphing calculator to integrate a definite integral. I know that we have varying calculator users. We've got a mixture of TI-84 people and TI-Inspire. I think probably most of you in the chat tonight are probably TI-84 with so many kids of Avon being out tonight. But you just need to let me know. Say something in the chat if you would like to see this particular setup. In fact, I'll tell you what I'm going to do. I've got my TI-84 emulator At least I thought I did. I'm going to go ahead and do this anyway. I've got something I want to kind of share with you. Okay. Would you mind, anybody from Franklin Central, Rachel, if you want to do this, could you tell me what kind of calculator that you guys use in the chat? I can't remember our conversations with Mr. Woodrow. I'm not sure. Mr. Passwater, you might know as well. So, meanwhile, I'm going to share something else. I'm going to share a graphing calculator. Are you ready for this? Sharing the main screen here. Okay, so if I go to this graphing calculator, one thing that I want you to be really comfortable with your calculator, if you're a TI-84 user, if you find yourself dealing with a free response question that you're going to revisit a function again and again and again, then I think that your best bet is to probably go into the Y equal menu. Yep, I wasn't ready for this, was I? Clear all these out. And it's probably to go ahead and enter that function in. This particular function was 2000 E, right? Oh my gosh, where's the E button? It's secant ln. And then we're going to raise that to the negative, and then we've got, we have a decision to make. You could use the letter T, but it's probably going to be a little bit more appropriate to use X, especially if you ever find yourself wanting to graph this. So a lot of times on the TI-84, I will always use X as my independent variable. If you're not sure of this little handy shortcut, alpha Y equal is pretty cool. It will generate a fraction, and then we can put our X squared over, what was it, 20? And then we can hit enter. That's going to be stored now, so that if we go to the quit screen, the calculation screen, we can do our wonderful math, what is it, 9? Math 9, all right? And we integrate from 0 up to 8. And now you don't have to type that function again. You just have to access it. And I think, guys, I'm not real good with the TI-84. I don't use it nearly as often, but I want to say it's alpha trace. Good guess, Mr. Record. So if we put that Y1 in there, it's kind of stored nicely. And again, I could have used the variable T, but X is going to work just as fine. And then that's going to give me a solution. Boy, it's a solution I hope is right. And it turns out that that's what I wanted. 783.6.195. So what we'll do here is I'm going to return back to the document, and making sure that the share, yep, the share went back to the document. And you're basically going to replace that expression with the integral with our good friend 7,836.195. I would probably advise you to try to round to a little bit more than 3 decimal places within the problem. It's not going to make a big difference here, though. And then, again, I'm going to curtail having to actually type this in the calculator, and I'm also going to tell you that you do not have to rewrite this. The only reason why I rewrote that is I wanted you to all see how this is coming together. Typically, what you would want to do on this problem is just return to your graphing calculator and say, oh, hey, I need to add that answer to 50,000, watch your decimal place or your number of digits, and then, oops, I got to subtract that water that just got drained out of the tank. And then, boom, that's the way that you can get your answer fast and easy. And you're going to be looking at 49,786. We like to see, did the problem ask you to round or anything? Let's return and see what it says. To the nearest leader. Oh, interesting. To the nearest leader. Let's go ahead and say, if you see on the AP exam that you should round, let's go ahead and round. Let's not take any chances there. I know sometimes it's frustrating and you might think that, it's inconsistent. Times that we don't round, there's times that we do round. Just make sure that you spend a little extra time, and before you leave any free response question, reread that part. Reread it very slowly and make sure that you've answered the question that was being addressed. Taking a look at the scoring rubric for C, how many points are we going to get for this guy? Whoa, here we go. C is worth 2 points, and you can see that having an integration set up, really the integral alone, just this guy alone, that guy and nothing else on your paper would warrant the first point. That's you understanding total amount of water accumulated. And then dealing with the other in and out aspect of this is going to give you the estimate. It goes without saying, if a student was really in a hurry and they didn't want to punch this into the calculator, that would be an acceptable answer. Don't forget your label. Even though it doesn't say we're going to award points for it, let's go ahead and put that. So we're going to finish up with the last part of this question. Again, I'm looking through the chat, and thanks, Rachel. TI-84s are the calculators for Franklin Central, and that's what I thought, so good. And if we read this guy, it says 4 times 0 to 8. Do we have a T when the rate at which the water is pumped into the tank is the same as the rate at which the water is removed from the tank? Please explain why or why not. Now, this might be a little bit trickier because this type of question is very likely going to sort of wrap its tendrils around a theorem that I know Mr. Passwater has gone over in class, a theorem that I know Mr. Woodrow has gone over in class, and it's a theorem that I have never told to my Avon students ever. Okay, that's a lie. I have. So we're probably looking at one of those very important existence theorems, those things like the intermediate value theorem or the mean value theorem. And that can be a challenge for students. All right. So I don't want to say, okay, we're going to concede this part because we've done pretty good on A, B, and C. Let's see if we can get something here. So is there a time when the water pumped in the tank is the same, the rate at which the water is pumped in the tank is the same as the water being removed? So you're basically comparing the W and the R. Now, one thing that you have pretty quick access of is at the very beginning of time, finding W of 0 and R of 0 is not a very difficult task. In fact, if we look up here, let's do the hard one first. W of 0 is 2000, is that right? You're replacing this T that I'm pointing to with 0. That's going to cause e to the 0 become 1, and we have 2000 as our rate. Okay, that was the hard one, you guys. Let's do the easy one. What's R of 0? Right here in the chart, 1340. So from that comparison, we can make the assumption, well, it's more than an assumption, but the rate at which the water is pumping into the tank is greater than the rate that it's coming out. So the tank's filling up. But then something might happen later on that changes that. And if you think about this a little bit, we could think, okay, maybe something drastically is happening way down here at the end. So maybe we could compare what's happening with W of 8 and R of 8. All right, so when we do this, and there's a variety of ways at which this can take place, but obviously if we just look at the graph, maybe we do the R of 8 first, we can see that we get 700. Boy, that was a big change, okay. But what is the W of 8? Well, we've got this model right here. Plugging 8 in is, well, that's going to be pretty tricky. Well, we do have a calculator. So what's nice about having that function stored, remember that name of that function? It was called y1, wasn't it? So we could just simply call up that function, y1, which was our W, and evaluate it at 8. And it's going to give us this 81-ish number, right? 81.524, in fact. So if we return, where am I? Part D. So if we return here, this is about 81-ish. I was getting ready to write ish. Maybe that's not good. How about 524? I don't want to give you guys some bad habits. So we see now that something has happened, and we see that the R has become bigger than the W. That was not the case before. And I want you to know that it's very likely this phenomenon may have happened much earlier than 8. It's very likely that it happens maybe at 6 or 3, but the fact remains you only have a few values of R that you can find, because there's no other way to be able to ascertain an R value unless you go from the table. Hopefully that makes sense to everybody. So just the sheer act here of seeing this change, we know that that means that W of t has to equal R of t at some point. Now, anybody have an idea of what theorem this represents? There's a lot of them out there. The good news is you don't have to name it by name. It's the intermediate value theorem, because it's basically saying that, you know, we went from sort of a negative correlation to a positive correlation. All right, therefore we had to stop at a 0 along the way. But the problem with this is that we would not earn full credit unless we state something prior to that theorem. And we have to understand that all of these existence theorems, the intermediate value theorem, the extreme value theorem, the mean value theorem, are all very predicated upon the fact that the function has to be continuous. And if we look in the problem, it's not like the question even ever told us that we had a continuous function. We were told that R was differentiable. We were given what W looks like. We can make guesses about that. So it's up to us to see that this phrase right here, this R is differentiable phrase, will imply R is continuous. And it's not going to take a lot of rocket science to probably figure out, hopefully, that W of t is continuous. In fact, that's something I just did today with the pre-calc class, talking about how exponential functions are continuous everywhere on their negative infinity to infinity domain. So you will need to make some kind of a statement either before W of t equal R of t or after, but just simply say W of t minus R of t, or vice versa, is continuous. Right? You know that that's true. If the two individual functions are continuous, their difference are going to be continuous. Now, if you really want to make this look super, you're probably good with the points here. You can say then, or therefore, yeah, you guys use therefore in your everyday life a lot. The intermediate value theorem, which is called IVT, guarantees that or says that R of t would be equivalent to W of t for some t. Again, I'm dressing this up probably a lot more formally than you guys would have to do, but we want to do that. We want to model a really good solution, but you have to understand that there are certain components of this would certainly be enough to earn the credit. Let's go ahead and take a look at the rubric here, and you'll see that this part's only going to be worth 2 points. That's all that was left. And it seems like we look very, very close together with my particular approach to this. Other approaches might talk more about the difference between W and R, and that's perfectly fine. The only thing that I did differently is I kind of added the R of 0 and the R of 8 over. As long as you consider some kind of comparison between W and R, you'd be in really good shape for this particular problem. Okay, I remember this well. I read this problem. And then the answer with explanation, the key components are mentioning the continuity and the fact that the W and the R are certainly going to be equivalent to each other. All right, so hopefully that makes some sense. Hopefully you guys feel confident in gaining a few points on a problem like this. So let's fast forward 2 years. How's that? We're going to go back to last year's exam. And we're going to take a look at our lovely tree question. Go back. So this would actually probably be on the first page. We're going to try to get through most of this. I don't want to keep you guys past 9, but I knew that tonight was going to be a little bit longer. We were able to do 2 problems last night, right on the hour. So let's read this one here. It says the height of the tree at time t is given by a twice differentiable function h. H of t is measured in meters. T is in years. Selected h's are given. So once again, use the data in the table to estimate h prime of 6. Use correct units, interpret what that means. Well, this probably sounds very familiar. You did the exact same thing on the previous problem. It's highly likely that a table question is going to ask a question such as this, and if it does, it's usually part A. It's a great way to get into the problem, feel very confident. So h prime of 6 in this particular instance would probably not be equal to, but maybe better yet, would be approximately equal to. But again, you don't have to say that. Give me a difference quotient right here at 6. How about 11 minus 6 over 7 minus 5? That looks good to me. You could stop right there, or you could simplify this to 5 halves. You're going to be getting a point for that. But then we have to do an interpretation with units. A lot of students ask, what if I put the units up here and not in the interpretation? As long as you have it in one place or the other, it's going to be fine. To be honest, it probably looks a little bit better in the interpretation, but you know what? If you want, put it both. I was going to say units. It's not units, right? What do we got here? If we took the derivative of meters over years, so we would have meters per year, you guys. Units. Yeah, that won't work. Don't write units. So the interpretation. Well, this is a rate of change. This tree is changing 5 meters, well, 5 halves meters for every year, right? So we could say the tree is growing, right? That would be okay. We could say the tree is growing or you could say the height of the tree is changing. The height of the tree is increasing, which is even more powerful. Or you could just say, in simple layman's terms, the tree is growing at a rate of 2.5 or 5 halves meters per year. But we're not there yet, guys. We're not there. Some teachers use this acronym. I didn't start using this acronym until this year, but I like it. NUT. Noun, units, time. You want to make sure that you have these 3 components, the noun or the number. That would be the fact that the tree is growing at a rate of 5 halves. That takes care of the N. The units, for the most part, is done here with the meters per year, but you got to have this time. That's the one that I think a lot of kids are going to neglect. Specifically, when is this a fact? Because I don't think this is a fact all the time. In fact, I can see right now this tree is only growing by 4/3 of a meter per year a little later on. So we have to say specifically at, oh, in a different color no less, that's fine. I'll just keep it purple. At the time t equals 6 years. Okay. My favorite preposition, you want to know it? It's at. I love using at whenever we are interpreting the meaning of a derivative, because that's a great preposition to denote instantaneously. Please avoid words like during or over a 6-year time span or something like that, because that will not earn the point. You would use prepositions like during or over if you're going to justify maybe one of these guys, right? An integral expression, during an 8-year or whatever period of time. All right, moving onward to part B. Oh, by the way, sorry, scoring rubric, almost forgot. Scoring rubric here. Let's cover this up. We don't want to spoil the ending of the movie, right? You guys don't want to know who dies in Endgame, do you? Well, I'm going to tell you. It's all right. So for A, we have 5 halves for h prime of 6, and then we've pretty much done a good job of stating the fact that the height of the tree is changing in meters per year. I don't know if Mr. Passwater is still on, but if he's even listening. But this is kind of interesting because this seems to kind of buck the trend of what had happened earlier about specifying a specific kind of change, in this case a positive number, using a positively charged word like increasing. Obviously they accepted this. I personally like to tell my students to try to use that positively charged word like increasing. Definitely use a negatively charged word if this were a negative number. Say something like decreasing, and I think you stand to have a better chance of making sure that you earn the point. But you guys, so much of it depends on who the question leader is and what their expectations are. So you can feel free to chime in if Mr. Passwater, if you want to do that. So going backwards, part B. Part B is going to ask us here to explain why there must be one time between 2 and 10 such that h prime of 2 is equal, or h prime of t is equal to 2. There are a lot of different ways to do this, and I could spend a lot of time talking about them. I've had students do this problem via the mean value theorem. I've had students do this problem via the intermediate value theorem. What I would like to do is maybe the most common thing, and then maybe it's common to me, but not everyone, but I would like to say that we could find a place along the interval 2 to 10 in this chart. So I'm going to scroll back up. Is there a difference quotient perhaps that's equivalent to 2? And you might have to subtract a few pairs of numbers to kind of see how that's playing out. Hopefully it's not going to be dealing with this thing, because I hate that number. Just 1.5, really? So if I keep looking hard enough, sorry, keep looking. What do I got here? What is that? 6 minus 2 over 5 minus 3. What is that? 4 over 2. Hey, I like that. I like that. So what I could do is say that my h of 5 minus my h of 3 over 5 minus 3 is equivalent to, well, 6 minus 2 over 2, right? 4 over 2, which is 2. So what I've got is a slope of 2 endpoints that's equivalent to 2. So that means that that's going to be equivalent to the h prime of t at that particular location. So I've got pretty much the conclusion of the mean value theorem. Now, the problem with this is a theorem. And if you're referencing a theorem, you must be very, very vocal in stating the criteria that had to be met. And the criteria that has to be met for the mean value theorem is that your function has to be two things. The function has to be both differentiable and continuous. We do not have to state that it's differentiable, because the stem of the problem says that. You're never going to earn points for stating something that's already in the stem. But we do have to know that differentiability implies continuity. Now, if you want to write that, that's great. That's great. It's probably a good idea. But on the scoring rubric for this problem, if a student said h of t is continuous, and if you were even more specific about it and said it was continuous on the interval over which we're evaluating, right, from 3 to 5, which was not necessary, then you've got that particular criteria satisfied. So since that's true, you can say therefore, or then, or thus, or as a result, or nothing at all, and just start writing. So therefore, by the mean value theorem, my pen is really a little shaky here, there is a C such that h prime of c is going to equal 2. And you may not even have to be so formal as this. We had a lot of students basically kind of refer back to this. We had students say h prime of t is equal to 2. And we allowed that. We allowed the spelling of c to be t. But what we didn't allow is for the student to not say continuous. So if we want to look really quickly at the scoring rubric here, the scoring rubric for this particular problem, there we see the point that's given just for a difference quotient that would be equivalent to 2. And then the second point is a conclusion that invokes either you writing the mean value theorem or just basically referencing what the mean value theorem is saying without using the phrase mean value theorem. Again, the derivative at the specific point is equal to the derivative or the slope at the two endpoints. You're going to end up earning that second point. Again, these can be challenging. We understand that as teachers. We understand that as readers also. You know, sometimes if you don't feel 100% confident with some of these theorems, you might be able to kind of back yourself into one of the points by just writing a claim that's accurate, that might start to open the door to that theorem. All right. Now, if we look at part C, it asks us to do another Riemann sum approximation. And this is now a trapezoid rule approximation, trapezoid sum, I should say, approximation, with the same 4 subintervals that we had in the previous problem. The thing about the trapezoid rule is, or the trapezoidal sum, is that you have to have a little bit more knowledge of a different shape. So in this particular problem, we'll have to kind of focus on the trapezoid idea, but then we're also, and this is a very tricky thing, you guys, we're going to have to really read this question. Approximate the, what's this phrase? Average height of the tree. The average value of the height of the tree. The average value of the function called height. Do you all see where I'm going with this? The average value of h on the interval 2 to 10. So what that is that special 1 over b minus a times the integration from 2 to 10 of the h of t. Now, if you're like a lot of students that I scored, they forgot the 1 over 8 in front. It's only going to sacrifice 1 point. All right, so I wouldn't worry a whole lot about that. I'm going to have to get rid of this timer, and the timer's not going to move. Isn't that great? Timer, go away. So what this is going to be equivalent to then with the trapezoid rule, it's an approximation. You don't have to say the approximate symbols, but we're going to start with our good friend, the 1/8, and then we're going to start gradually putting together our trapezoid rule formula. And that's simply taking 1/2 times the sum of the 2 bases, which are going to be comprised by these 2 numbers here, 1.5 plus 2. Might need a little more room here. And then we're going to multiply that by the height of this particular trapezoid, which is the distance 2 to 3. And you're just going to keep up that same routine. About this time, I look and say, gosh darn it, I could have factored that 1/2 out in front because we keep using it over and over again, but that's okay. You only have to write it 4 times. Luckily, we see that we have a varying width, so having factored out that would have not worked. The height here is 2. And then one more area of a trapezoid expression, 1/2 of 11 plus 15 multiplied by 3. That's a pretty messy expression, but it will earn you a point. In fact, it will earn you both points. It does not have to be simplified. This particular problem is number 4, which means you do not have a calculator. I'm probably leaning more towards the camp of not simplifying this. Unless you have just a lot of time on your hands and you really, really want this simplified, it's probably not worth it. Maybe you come back to this at the end of all of the free response questions and you very slowly go about the process. But it turns out that it's going to be pretty ugly anyway. And it's interesting that some students did put this into their calculator and got like 65 3/4 or 65.75, still multiplied by 1/8. That was a really common answer for this. And the overachievers in the group, right? We got some of you out there, I know, you'd have 263 over 32, but you guys, the fact is it was a very ugly answer. And I'll be straight up honest with you, when I took this problem 48 hours after it was released and I solved it, I thought, okay, I screwed up somewhere. That can't be the right result, but it was. I typed it into a calculator to verify. All right. It is the average height of the tree. So if you want to think about what the label would be, I guess the thought process would be, well, you've got something that's in meters right now for the h, and you've got something that's in years for the dt, but you just divide it by a time out in front, years, so those years are going to cancel. So the units would be meters, but you wouldn't need to express that. That wasn't part necessarily of the scoring rubric, but it's nice if you guys do put that. All right. Haven't looked at the scoring rubric in a while. It probably looks a little similar to what we did. Whoops, one screen too far. And yeah, we got our initial integration set up, just kind of making sure that we do this the right way. You don't have to write this. Students did not have to put either of these. As long as you introduced with this, you would be clear for both of the points. Again, like we said, it's nice to identify things, so we love to see that left side. We love to see this written out. But you get 1 point for the trap rule, or the trapezoid sum, I should say, and then the approximation in blue kind of takes care of both of those. You were allowed to make a mistake or two in this trapezoidal setup. You would still earn the trapezoid sum, but you would forfeit the approximation sum. And it's very likely that you would want to say something along the lines of, well, that I want to say something along the lines of, if a student, let's say we have a student who really struggles with the trapezoid rule, or the trapezoid sum. It's tough. There's a lot of stuff going on. But maybe you are really super strong with the left endpoint and the right endpoint rule. You see those all the time. I'm sure that many of you are aware that if you did the left Riemann sum, okay, much like we did in the previous problem, calculated the right Riemann sum, added them together and divided by 2, which is the same thing as finding the average, that will every time, without exception, be the trapezoidal sum. So that will work, right? If you feel like you're getting nervous and you don't feel like you've got the confidence with the trapezoid rule, average the left and right. Now, it will take a little bit more time, so make sure that you're aware of that. But I graded several papers. In fact, I would grade them in clumps, one after another, which is pretty indicative of the teacher using that as their strategy. All right, I know that we're over a little bit. If anybody has to pop out of the session, I completely understand, but I want to go ahead and do this last part because it's got a very interesting concept associated with it, one that we might talk a little bit more about next Thursday. But now it says we got the height of the tree in meters that can be modeled by the function g given by this guy. X is the diameter of the base. The tree is 50 meters tall. The diameter of the base of the tree is increasing at a rate of 0.03 meters per year. According to the model, what is the rate of change of the height of the tree with respect to time when the tree is 50 meters tall? Again, so much text, so much text. Just kind of isolate in on what is it that we're trying to find? What is the rate of change of the height of the tree? So you want to find the derivative of something, right? That's a rate of change. Now the height of the tree, it's got a different name now. It's no longer h, right? We're tired of using that table. That table was not very accurate. Some other botanist has come in and they've done some research and they said, no, this tree is growing by this rate g of x. So we're going to take the derivative of g, but with respect to what variable? Time. So that would be dg dt. That's what we're going for here. Now that can carry a lot of weight. If you see that and you go back up here and notice that, okay, I can take the derivative of this g, hopefully I can take it with respect to t, you're going to be able to use most likely the quotient rule. There are other alternatives if students want to bring the 1 plus x up to the numerator and use a product rule, but I'm going to go ahead and stick with the quotient rule. So dg dt is what I'm so interested in finding here, is going to be, well, how does the quotient rule go? Gosh, it's been a long time. I forgot. I might need help with this. Derivative of the top is 100, but because I have the variable x and not the variable t, I have to tack on my good friend dx dt. So there's the derivative of the top, multiplied by the derivative of the bottom. Then, very important, we do need to subtract. This is a quotient rule after all. And then we have the numerator, 100x, And now we'll multiply that by the derivative of the denominator, which is 0 plus, okay, what is the derivative of x with respect to t? That's a brain teaser, right? The derivative of x with, I think it's the derivative of x with respect to t, right? It's 1 times dx over dt. And then, of course, all of this would be on top of the denominator squared, which is 1 plus x quantity squared. All right? You'll be surprised here in a moment how many points you would be awarded for that. Now, if you haven't figured it out by now, this is your favorite problem in all of calculus. I know some of you have been through related rates. I know some of you might be just started to kind of do some fine tuning and you're going to review this idea. But really a related rate problem is just taking this idea of a derivative with respect to a time and giving it some context in the real world. Right, so it's not something that you should really be fearful for. A lot of kids think, oh gosh, related rates are so difficult. They really aren't. And what we're going to do is just plug in the information that we know, right? All we got to do is figure out, well, what are we going to use for x? What are we going to use for dx dt? And if we figure those two things out, we've got this problem licked. So x, what does x stand for? I forgot. Let's read. X is the diameter of the base of the tree. Okay, I got it. But what is that x at this instant? We're dealing with when the tree is 50 meters tall. Oh, does that mean x is 50? Is tall diameter? No, tall is height. So a student would have to make that connection, and I'm going to use a different color so it stands out, and you would have to set 50 equal to 100x over 1 plus x. That's a pretty easy thing to solve. I just don't have a lot of room. My stupid timer's in the way. So if I cross multiply, 50 plus 50x would equal 100x. We will soon come to the realization that x is 1. And that's what's going to replace these three x's. Now, believe me, a lot of kids put a 50 in those spots. There was a deduction. They're not going to get the right answer, but 1 is what we want. And then the dx dt, think sort of contextually, what does dx dt mean? It would be the rate of change of the x, right, which is the diameter. Any information in the problem about rate of change of diameter? Let's kind of highlight the diameter of the base. Oh, it'd be great if I had a bigger highlighter. The diameter of the base is increasing at a rate of 0.03. There you go. Your dx dt is going to be 0.03. So when all of this is put together, you have 100 times 0.03. Not a big fan of 0.03. I'm a bigger fan of 3 over 100, I'll be honest. X is 1, we've already talked about that. X is 1 again, I'm just going to write 100. And then we got another 3 over 100 here. We could have factored out that dx dt as well. And the denominator is, I want to say it's 4. Is that right? 1 plus 1 squared. And then this thing will simplify pretty nicely. The hundreds cancel. You got 6 minus 3, which is 3 over 4. And now you've got your dg dt. I would certainly entertain the thought of putting a label. I'll be honest, it does say the label in the problem. If that's the case, then you're not going to be held responsible for the label in your answer, but why not? Right? There's nothing wrong with that. There's nothing wrong with always double checking the labels of your contextual problems. All right. So we got 3/4 meters per year. And if we look at the scoring rubric for this, it's probably pretty orthodox. The only thing they did differently is they found that value of x a little earlier. Here's their quotient rule work. They did something different than I did. They simplified the quotient first and then they plugged in, but you're going to get the right answer either way. But you can see the premium placed on that derivative. Big time. 2 points is a pretty nice derivative there. I remember that the 2 points were divisible. In other words, if a student successfully showed the quotient rule they would automatically earn one of those 2 points. The other point was this chain rule piece, just knowing that there was a dx dt attached to the problem. And of course, the answer was, either the 3/4 or something that's numerical, that's equivalent to 3/4. So I apologize, we're 12 minutes over. That's terrible, isn't it? It's bad, that's bad. I am going to go ahead and I'm going to stop the recording. Thanks for those of you that are watching this via tape delayed, HBO Now, Amazon Prime, or just YouTube, I guess. We'll have another video very soon tomorrow night with Mr. Passwater taking over. So thanks for watching.